In this video, we're going to talk about a divide and conquer sorting algorithm called Mergesort. Mergesort is a comparison-based sorting algorithm with worst-case running time theta of n log n. That means it always finishes in time order n log n for every input, and there exists inputs for which it takes time omega of n log n to finish. This running time is optimal for a comparison-based sorting method. So any comparison-based sorting method is always going to take worst-case time omega of n log n. Mergesort is a stable sorting algorithm, but is not in place. So we're actually going to use an auxiliary vector of the same size as the input vector during the algorithm. Mergesort is also a great example of a divide and conquer algorithm. When we talked about insertion sort, we saw that the key subroutine of the algorithm was inserting an element into an already sorted array. In Mergesort, the key subroutine is the following. We are given an array where the first half is already sorted and the second half is already sorted. So in this example, you see that the blue section is already sorted and the red section is already sorted. The goal of the merge subroutine is to merge these two sorted arrays so that the entire array is sorted, as in the picture at the bottom. So we want to go from the picture at the top into the picture at the bottom. We want to merge the sorted first half with the sorted second half. So let's go into more detail about the specification of the merge function. In general, we're going to have a vector vec, and we are focused on a particular interval of this vector. So that's the blue and red colored portions of the picture. We are given three iterators into this vector, low, mid, and high. We are promised that the vector is already sorted in the interval starting from low and going up to but not including mid. So you see that defines the blue region of the vector. This is called a half-closed interval. It contains the starting point but not the ending point. This is the kind of interval that's typically used in C++. So just as vec.end points to one past the end of the vector, so you usually do not want to include what's pointed to by vec.end in your algorithm. So we stick with this convention in defining our merge function here and work with half-closed intervals. So we're also promised that vec is sorted in the half-closed interval from mid up to but not including high. The goal of the merge function is to sort the vector in the half-closed interval from low up to but not including high. So here's the signature of the merge function. I have a using declaration here to save space so I don't have to keep writing standard vector of int : iterator. That makes everything hard to fit on the slide. So the using declaration abbreviates that to just vec it. For this example, we are assuming that we just have a vector of ints. The merge function takes three iterators, low, mid, and high. And again, the assumptions are that the vector is sorted in the half-closed interval from low up to but not including mid, and from mid up to but not including high. At the end of the merge function, the vector should be sorted in the half-closed interval from low up to but not including high. As we are giving iterators to the vector, we can directly modify the vector, and we do not need to return anything, so the return type is void. The merge function can be implemented to run in time theta of high minus low, and to use theta of high minus low additional space. The merge function is the reason why Mergesort is not an in-place algorithm. We use an auxiliary array, an auxiliary vector of size high minus low in order to implement the merge function. So I'm going to leave the implementation of the merge function as an exercise for tutorial. So now let's continue developing Mergesort, where we just take the merge function as a black box. Okay, so now we've seen the merge function. How can we make use of the merge function to construct a sorting algorithm? Well, first we're going to separately consider the left half of the vector and the right half of the vector. This is the divide step. Then we're going to sort the left half and sort the right half. We then combine the two sorted halves into a fully sorted vector using the merge function. This algorithm outline should leave you asking a question. How do we sort the left and right halves? Sorting the left half of the vector is exactly the same problem that we started with, sorting a vector. Since it's the same problem, we can use the same algorithm. So we're going to recursively call Mergesort to sort the left and right halves. Let's put Mergesort back in the context of a divide and conquer algorithm. Our original problem is to sort a vector of size n. We divide this into two subproblems, to sort the first half and to sort the second half. Thus we have two subproblems of size roughly n over 2. After solving these subproblems, the first half of the vector is sorted and the second half is sorted. Now remember that we divided up the work in a divide and conquer algorithm, apart from the solving of the subproblems, into three categories: create, complete, and combine. So let's look at the work that we have to do in these three categories for Mergesort. The create step is to create the subproblems. In Mergesort, the subproblems are just the first half of the vector and the second half of the vector. So it's very easy to create the subproblems. All we have to do is to compute the midpoint of the interval that we're considering. And for the complete step, there's actually nothing that we have to do. All the information that we need to sort the vector is contained in the subproblems. The combine step is to combine solutions to the subproblems to solve the original problem. And this is where the main work of Mergesort occurs. The combine step is exactly what the merge function does, right? It takes the solutions to the subproblems, so the first half of the vector is sorted and the second half of the vector is sorted, and it combines these to produce a vector that is totally sorted. Okay, so here's the Mergesort function in code. We take two iterator parameters, begin and end, and the function will sort the vector in the half-closed interval starting at begin and going up to but not including end. So that's the goal of the algorithm. The first three lines of the function handle the base case of the recursion. If the size of the vector is at most 1, then it's already sorted and there's nothing to do. In this case, we can just return. So if we let t of n be the running time of Mergesort when end minus begin is equal to n, then we see that in this base case, we just spend constant time. In the next line, we define an iterator mid, which points to the midpoint between begin and end. So this is the create step, where we define the subproblems. And this step also just takes constant time. In the next line, we sort the left half of the interval between begin and end. We do this by recursively calling Mergesort with the arguments begin and mid. Remember that this will sort the interval from begin up to but not including mid. In the following line, we recursively sort the right half by calling Mergesort with arguments mid and end. This will sort the portion of the vector starting from mid and going up to but not including end. The running time of these two steps will be t of mid minus begin plus t of end minus mid. So roughly, if the original vector has size n, the original interval has size n, these two steps will take time 2 times n over 2. When we arrive at the last line of the function, the vector is already sorted in the half-closed interval from begin to mid and in the half-closed interval from mid to end. Now we are at the combine step. We combine the solutions to the subproblems into a solution to the original problem by using the merge function to merge these sorted intervals. The merge function can be implemented in time proportional to the size of the two vectors to be merged. So in this case, a constant times end minus begin. So this step takes time order end minus begin. So the total time for this function is t of mid minus begin for the first recursive call, t of end minus mid for the second recursive call, plus order end minus begin for the combined step that is calling the merge function, plus a constant to handle, checking for the base case and creating the intervals, so defining this variable mid. We can just ignore this constant because it will be subsumed by the order end minus begin term. So now we have a recurrence relation for the running time of Mergesort. I'm going to assume that n is a power of 2 to simplify the recurrence. Then the time to merge sort a vector of size n is 2 times the time to merge sort a vector of size n over 2 plus a term of order n for the merge function. The base case, when the vector has size 1, takes constant time. So this is exactly the same recurrence we had in the buy and sell stock problem. So we know that the solution is order n log n. So that tells us that the running time of merge sort is order n log n.